Hey folks, nothing lasts forever except for infinite series, and they they just go on forever. They really do go on forever. Eventually, we're all going to be able to go out and go to a ball game or something. But right now, the only infinite thing that we have is infinite series. And in particular, we want to talk about Taylor and Maclaurin series. These are power series that can be pretty easy to construct and give you some real insight into how to use some of the functions that we use every day. So these are pretty important. The basic idea is that you have a power series, which I am writing out. One thing you get from power series is maybe developing a little bit of patience, because they take forever. So I'm writing this in two forms. The pardon me, summation notation, and just writing out the first few terms. And this is great, except what if you don't know what's going on? I need to show you one more thing, which is the difference between Taylor series and Maclaurin series. If you evaluate this function someplace else, then the standard ways of translating functions applies. This is one of the best ways to think about this. So f of x minus c, I should say f of x minus c. Well, what you're going to do is have the same structure, do the parentheses first. This is going to look a little bit like a crazy person did it because they didn't leave enough room. So do the parentheses first, and wherever you have an x, well, now you have x minus c. I already did that one. Okay. So that's all. So this is a Taylor series. Maclaurin series is where c is 0. So let's see if we can get a handle on some of these coefficients. And what we do is take the derivative term by term, and then take the derivative term by term, and then take the derivative term by term, and then take the derivative term by term. Goes on forever. It really does go on forever. And we're not solving some of our problems, but we're kicking them down the road. And so hopefully we'll be able to do things. So f prime of x is a1 plus 2 times a2 times x plus 3 times a3 times x squared, and then we're going to continue in that same pattern, and that's just taking the derivative. Derivative constant is 0, derivative a1 times x is a1, derivative a2 times x squared is 2a2 times x2. Same old derivatives, we're just going to do an infinite number of them, okay? The thing to make a note of here, and this is kind of what makes it go, is I'll just kind of keep a tally down by the side. F of 0 is a sub 0, and f prime of 0 is a sub 1. Ooh, that looks pretty good. Right, so f of 0, all these other terms are 0 except for the constant. F prime of 0, all these terms are 0 except for the constant. Now, when we take the second derivative, we're going to start to see what the pattern is. The second derivative is, well, now the derivative of that constant that started at a1 is still 0. So you have 2 times a2 plus 2 times 3 times a3 times x plus 3 times 4 times a4 times x squared. And then we're going to continue in that pattern. What exactly is that pattern? Second derivative, 2 factors, and the indices are the subscript and 1 before the subscript, and the power is 2 before the subscript. So there's the second derivative. Now when you plug in 0, everything is 0 except for this 2a2 term. And now the pattern is going to start to emerge even more strongly. When we take the third derivative, the constant goes away, and we have 2 times 3 times a3 plus 2 times 3 times 4 times a4 times x plus 3 times 4 times 5 times a5 times x squared, so forth and so on. So the pattern is third derivative, 3 factors, and again you count down from the index. Index is a4, and you count down 4, 3, 2, and the exponent is 1. Count down 5, 4, 3, and the exponent is 2. So there's the pattern. And again, when x is 0, all this stuff goes away, and you have 2 times 3 times a3. And if we just imagine what's going to go on next, what's going to happen is we're going to pull down a factor of 2 when we take the derivative of this term. And so the fourth derivative, remember there's a special notation for fourth derivative, is going to start with 2 times 3 times 4 times a4, and then a bunch of terms that have x in them, so I'm not even going to bother to write them out. So let me write down the values that we see so far, and then we're going to be able to jump to a conclusion. Third derivative is 2 times 3 times a3. Fourth derivative at 0 is 2 times 3 times 4 times a4. And we can jump ahead to the nth derivative. We really have kicked the can down the road here. We're talking about the 71st derivative or something. Is n factorial times a sub n. That's not so useful. You know what's useful is turning that around, which is to say that a sub n is a fraction. The top is the nth derivative as 0. Not the nth derivative, that's a function. The nth derivative is 0, that's a number, divided by n factorial. And so this is the big formula that we've gotten here by following these patterns. And what you're paying attention to is the pattern here. Third derivative, 3 terms. Fourth derivative, 4 terms. Fifth derivative, 5 terms. 12th derivative, 12. I'm sorry, I'm saying terms and I mean factors. Okay. So if we put this into action, the first thing that you want to do this with is the exponential function, because f sub n of x, it doesn't matter what x is still e to the x. The derivative of e to the x is e to the x, and the derivative of e to the x is e to the x, and the derivative of e to the x is e to the x, and you just keep going like that forever, much longer than this lockdown is going to last. And so when you evaluate that as 0, you get e to the 0. So everything that comes up here, all the tops of these are 1, and so you just get 1 over n factorial. A sub n is 1 over n factorial, and e to the x is, I'm just going to write it this way, is the sum n equals 0 to infinity of a fraction x to the n over n factorial. 0 factorial is taken to be 1, and so we're not dividing by 0 there. So this is one of the most important power series. This is probably the most important power series, let's be honest, folks. And it comes from the fact that the derivative of e to the x is e to the x, so the second derivative of e to the x is e to the x, so the third derivative of e to the x is e to the x. Stop me before I hurt myself. Bingo. And the other thing is that n factorial is really big. 10 factorial is more than 3 million, so you just do a few terms of this, and you've got a very accurate estimate of e to the x. It's kind of a pain. I mean, 10 terms is going to get you like 5 decimal places worth, but so that's not going to be no work, but it's something that's worthwhile. So I'm going to quit here with this. What we have is the general pattern of the coefficients, turning that around to get a formula for the coefficients, and the first application. Next application will be logarithm, and so start with this and enjoy.